All right, mathematicians, let's get started with section 4.2 about reflections. Our essential question, how can you reflect a figure in a coordinate plane? Our objectives, mathematicians will be able to perform reflections, perform glide reflections, and solve real-life problems involving reflections. All right, let's take a look at performing reflections. It's a transformation in which all points of a figure are reflected over a particular line of reflection. So our lines of reflection are in gold. You can fold along the line to reflect. And main thing that we want to see is that your lines of reflection have equal points from each vertices. So I can see that this vertex is same distance on both sides of the reflection. So as long as every vertex is the same distance on both sides of the reflection line, you've done your reflection correctly. So folding along the line of reflection is one strategy. So let's take a look at these two images. We can fold along the line of reflection as one strategy, but we need this point on this side and these two vertices on this side. And then this one's pretty unique. So if you folded your paper and kind of traced, you should have ended up with this dashed image for the copy of the solid. The solid is your pre-image. And since this one mapped onto itself, you don't see the second image because it's exactly on top of itself. All right, so the image is congruent to the pre-image, so a reflection is an isometry. Let's see if we can look at these two situations and come up with our line of reflection. So folding, you can fold the two images to see if you can figure out the line of reflection. So it looks like it would be something along this line diagonally, and this one doesn't look like it has a line of reflection. So there we go, there's our two lines. This one goes diagonally, and then this one doesn't have a line of reflection. So let's take a look at key point number 1, our reflections. They are transformations that use a line like a mirror to reflect a figure. That line of reflection, in other words, our mirror line, is our line of reflection. We have coordinate notation for a reflection, in other words, our rules. We can reflect about the x-axis, which means the points will change only for the b value. In other words, the y-coordinate is the opposite. X stays the same. In other words, a stays the same. If I reflect across the y-axis, or about the y-axis, my points become opposite for the first value, so the a value is opposite, but the b value stays the same. About the line y equals x, also known as the parent linear function, I switch my values. About the line y equals negative x, I will switch and opposite for both. And here are some things that are true for our reflection. A reflection in a line maps every point in the plane to its copy or its image, so that each point one of the following properties is true. If P is not on line M, then M is the perpendicular bisector of segment P to P prime. Or if point P is on the line, then P equals P prime. And here's our two illustrations of these 2 points. All right, so let's take a look at coordinate example 1, reflecting in the horizontal and vertical lines. So graph triangle ABC at the following vertices and its image after the reflection described. First, we want to reflect in the line N located at x equals 3. So remember, this is a vertical line. So my line is located here vertically. So VUX, remember from our previous unit, can help us with our vertical lines. They're the special lines, and they go vertical at x equals 3, so find 3 on the x-axis and then do a vertical line. Now graph A, B, and C. Now we're going to reflect across this line. Remember, you want same distance on both sides. So A is 2 away from this side, so it needs to be 2 away on the other side. And then B is 2 from the line of reflection on the right, so it needs to be 2 away on the left. So I'd plot here. And then C is 1 away on the left side, so it needs to be 1 away on the right side. So when I connect A, B, C prime, it should look something like this. All right, here's a cleaner version of example A. Let's move on to example B. We want to reflect across the line y equals 1. All right, so that's our acronym is HOI. These are horizontal lines. So I should be graphing it horizontally at 1. So find 1 on the y-axis and then draw a horizontal line through that point. So with that same triangle, all right, so there's triangle ABC. So this time, A is 2 above the line of reflection, so it needs to be 2 below when I reflect. So A will map here for A prime. Looks like B is 1 above, so it needs to be 1 below. So B prime will land here. And then C is on the line, so C prime will map onto itself, 0 distance. So it's going to be on the line. So there's your second image. Here's a cleaner version of example B. Our next example, we're going to graph segment FG with endpoints at -1, 2, and 1, 2, and its image after a reflection in the line y equals x. All right, so there's our parent linear function, y equals x. And we need to plot our points F and G. All right, so we need to reflect FG, segment FG across this line, y equals x. So you can always fold your paper as a strategy. But I like to look at the distance away from my line. So it looks like my line is going diagonally. I can count diagonally 1 and then a half. So I can go half and then a 1. So that means F prime is going to map right here at 2, -1. And then G is only half, so it needs to go half on the other side. So G reflected here and then connect. Here's a little bit clearer image of the reflection of segment FG across this line y equals x. All right, so key point number 2 is our coordinate rules for reflections. So if I'm reflecting across the x-axis, my rule is that A stays the same, but B is the opposite. So let's take a look at some examples. The point 3, 1 pre-image would become 3, -1. If I reflect across the y-axis, let's take that same point, and it would become -3, 1. So only the A value is the opposite, B value stays the same. If I reflect across the line y equals x, they switch, so it becomes 1, 3. And if I reflect across the line y equals -x, it switches and becomes opposite for both values. So one way to help us with our rules is our implied statement. So the pre-image AB reflects the x-axis to become image A -B. And if I reflect across the y-axis, it becomes image -A, B. And if I reflect across the line y equals x, I switch, so B, A. And if it reflects across the line y equals -x, it switches and is opposite, -B, A. All right, so let's take a look at example number 3, graph segment FG from example 2 and its image after reflection in the line y equals -x. So here are our coordinates from example 2, so we're going to plot those on our grid. Now a reflection across the line y equals -x means I switch and opposites. So let's check out what our coordinates, new coordinates will be. For the coordinate F, it goes from -1, 2 to becoming -2, +1. Again, switch and opposite. For G, it becomes -2, -1. So here's our line y equals -x. Here's what our reflection across this line should look like. So after you figured out your coordinates, you can plot them and then connect. And since this is our line y equals -x, I should see equal distance on each side to the reflection line. And you can also fold your paper along the reflection line. That's another strategy you could use. All right, so here's our reflection postulate. It's a reflection, which is a rigid motion, in other words, isometry. We learned this from the previous lesson. It means we maintain length and angle measure. So our implied reflection implies rigid motion, in other words, isometry. So we know that the following statements are true for any image. Specifically, this situation, triangle DEF, mapped onto D prime, E prime, F prime. We maintain length, so the length from D to E is equal to the length from D prime to E prime. So all of our segment lengths for the object that we're reflecting maintains length and angle measure, as we can see in our statements here. A glide reflection is a transformation involving a translation followed by a reflection. Here would be your steps, and here's an illustration. Step 1, first you would translate your image onto its pre-image onto an image. So for example, P becomes P prime. So it translated up and to the right. Q also translates up and to the right. So translation happens first, and then a reflection in a line K parallel to the direction of the translation. So this line represents the parallel to the direction, in other words, your vector, and you would then reflect across this line. So this is the result of a glide reflection. Glide is your translate, and then reflect. All right, let's perform a glide reflection with example 4. Graph triangle ABC at the following vertices, 3, 2, 6, 3, and 7, 1. And then we're going to translate according to this rule. Our rule is that we're going to move to the left 12, and then there's no change in the y-coordinates, so we will not move up or down. And then we're going to reflect in the x-axis. So we start by graphing our pre-image, so it should look something like this. And we do a translation, in other words, we glide first. So we're going to translate all of these coordinates to the left 12. So this one's going to move all the way over to, so 3 minus 12 should put you at -9, and then nothing changes on the y. So I should end up at -9, 2 for A prime, and then this one should end up at -5, 1, and this one should end up at -6, 3. So the results should look something like this. So A prime, B prime, and C prime, and then I'm going to reflect across the x-axis. So remember, the distance should be the same from the line of reflection. So x-axis is the line of reflection. So I'm 2 away for this vertices, so I should be 2 away on this side. So I should be at -9, -2. Then this one should be 3 away, so it should be 3 away this way. So I'll be at -6, -3. And then here, this one would be at -5, -1. So there is your completed glide reflection. All right, next we have identifying lines of symmetry. So lines of symmetry is a figure mapped onto itself by a reflection line. And then the actual line of symmetry is the line of reflection. So line symmetry is when you can map a figure onto itself by some reflection line. And then we have lines of symmetry, which is the actual line of reflection. So let's see how many lines of symmetry we can get with this figure. So how many different lines can I get and this figure can map onto itself? Well, for sure I can do a horizontal one right through here, and I can do a vertical one. So this for sure has 2 lines of symmetry. So I can do one right through there and then one right through there. And then for the next figure, I can do one right through here and one right through here. And then looks like I can do one through every vertex. So this one has a total of 6. This one, I can map that one onto itself, and looks like that's it. So for part A, I could come up with two lines of symmetry. For the next one, looks like we had 1, 2, 3, 4, 5, 6, 7, 8. Wait, I'm counting some of the same lines, I think. So let's back up. Can't count that one again. Can't count that one again. But there we go. Okay, so I have 6 total lines of symmetry, and this one only has 1. That's all for this lesson. Bring any clarifying questions into class, and we'll practice together. I leave you with this note from Optimus Prime.
Autobots, transform and roll out.